My Earth Science Faithful video number 2. Today we're going to get into winds and what's going on with wind. Okay, so what causes wind? It's caused first by the differences in pressure. Okay, high pressure, I believe it's going to go from high pressure to low pressure. We use an anemometer to measure wind speed or wind velocity. Okay. And then this is the tricky part, how we name these things. The wind is always named for the direction from which it comes from. So you've heard of a northeaster or prevailing northeast winds, that kind of stuff. It means it's coming from the northeast. So here is a picture, and this is in the bottom of your notes. It's on the top page of the next page. You're going to want to take a little bit of notes, and then we're going to get into the Coriolis effect. Okay, so, whoops. Here is the northeast. And you'll see the northeast is going to be at about 45 degrees. Okay, and it has southwest winds. Do you see that's coming from the southwest? So it's going northeast, so it's coming from the southwest. And that probably shows up opposite in your video compared to what my hands are seeing. And the opposite's true in between 0 and 30 degrees north. It's got northeast winds, right? And this is right in your reference table, I believe. So 45 degrees north, I'm coming from the southwest. So 45 degrees north is where this picture is actually pointing. Okay. 45 degrees south is going to be the opposite. So when I look at 45 degrees south on the picture, I can tell that it's going to be a northwesterly wind. Yay, because it's got to be in between the 30 south and 60 south. So 75 north has got to be above the 60. So I see northeastern. And then 20 degrees north is got to be in between 0 and 30. So it's got to be also northeastern. Yeah, it's just me reading where the latitudes are on that chart. So that's how we do that. Is there rising or sinking at the equator? Nice. So air is rising. See, it's going up. So air is rising at the equator. Definitely need to know that. And is air rising or sinking at 30 degrees north? That's that where it says dry, 30 degrees north. And that is where air is sinking. Based on this picture. Wow. Okay. Cool. Now I'm going to, these are some videos about the Coriolis effect. They're really neat. So I'm going to mute this so you can hear that. Ready? Go.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low-pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise, and that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving this example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video, and that's kind of the point. I hope you got what you came for. And the Coriolis effect doesn't really influence toilets, they're just really too small, and the direction of the spin more depends on the placements of jets inside the toilet. But that's it, that's the Coriolis effect. If you liked this short and to the point video, give this video a like, and if you want to see more videos like it, why not subscribe? I'll be back next week with another.
Okay, so I hope that helps explain it a little bit. There's actually one more video that I like that's going to help really explain it, but you do have to write this, by the way, if you didn't. Right, the deflection of the winds and surface ocean currents. Okay, under Coriolis effect, you need to write that. And then there's one more video. This video is also very neat, so let's try this one.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion.
Right, here's the game, right? You're going to throw the ball straight. So what's your name? Victor, right? Yeah. But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah, I don't know.
Right, what's going to happen, dude?
I was going to veer off to the left.
So the ball is going to swerve off to the left.
Yep,
And you might catch it.
possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, is that everyone? No, hang on, one more. Spencer,
He's not arrogant.
just quietly
He's
confident.
not catching it. He's
Really?
not catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying to come to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
Right, in your own time, throw the ball.
I got this. Oh!
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw?
Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, I did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we're all agreeing here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
Nope.
No idea.
It's called the Coriolis effect. And it's very simple. It's objects in motion it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight. It's still going straight, but the table is moving below you. And all of a sudden, look who's in front of that straight moving ball. And it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to. And that, ladies and gentlemen, is the Coriolis effect.
With a simple game of
So I hope that helps you understand Coriolis effect just a wee bit. There we go. Oh, this is important. This is convection cell. You need to know wind blows from areas of high pressure to areas of a low pressure. You do need to know that too, and you need to write that in there. Okay. Good. All right. And then we got to get into high pressure, low pressure systems and what they're going to look like. But we'll do that next video. This one was long enough.